and I have known Jin-Yi for 7 years. And Jin-Yi holds a bachelor's degree from National Taiwan University. He earned his PhD from the University of Washington. And following his doctoral study, Jin-Yi undertook research in UC Los Angeles for 10 years. His commitment led him to UC Irvine, where he now holds a professorship. Jin-Yi is recognized for his study of El Niño diversity and complexity, particularly for introducing two types of El Niño in his 2009 study. And this study has been cited over 1,700 times. And now I think let's join me to welcome Jin-Yi to talk about the 21st century El Niño. Yeah, Jin-Yi, the screen is all yours.
Okay, thank you. Yeah, first I'd like to thank Dr. Sanhe for the introduction and invitation. So I'm pleased to have this opportunity to tell you a research idea that I have been developing during the past about 10, 15 years. That is that I want to propose or argue that the El Nino we encounter in the 21st century, so far in the 21st century, are not the same El Nino that we study in the 20th centuries. And it is because the 21st century El Nino has a very different property, different generation mechanism, and different climate impact from the El Nino we know in the 20th century. So I hope I'm going to convince you on this idea. So we all know that El Nino is referring to the warming of sea surface temperature in the tropical Pacific. And in the 20th century, typically, most of El Nino started warming somewhere in the South American coast and extend westward. When El Nino died, it will return back, the warm water back to the South American coast. That's what I'm showing here for the 1997-98 El Nino event. But occasionally, in the 20th century, we already noticed that some El Nino event has its warm water pop up directly near the Central Pacific Ocean region, near this White Line International Day 9, like what I'm showing here for the 1977-78 event. You can see that throughout this whole event, there's no warm water coming out from South American coast. Instead, we see that warm water around this International Day 9 at the equator actually connect to warm water coming out from North America. However, because this kind of event didn't happen very often in the 20th centuries, so at that time, we didn't think that this kind of event is so different from this typical 97-98 El Nino coming from the South American coast. We just thought that they have the same physical mechanism, same generation mechanism, just sometimes the generation mechanism will move the warm water from South American coast occasionally to International Day 9. So it was not receiving a lot of attention in the ENSO research during 20th century. However, after we enter the 21st century, we noticed that this kind of El Nino warming near the International Day 9 happen more and more often. Actually, so far we have a total of 7 El Nino events. All of them either completely look like this Central Pacific El Nino warming or have some signature related to this warming. So let me quickly go through these 7 events to convince you on this argument. So the first 2 events we have in the 21st century is 2002 and 2004. So I'm showing both events in this animation. You can see that warm water throughout these 2 events always have this red color showing up in this white line, which is International Day 9. So we didn't see much warm water coming out from South American coast. And when we come to the third event, which is 2006 and 7 event, is more interesting. You can see that here, International Day 9 180, you can look at throughout the life cycle of this event from beginning to it die. You can see, you always see warm water continue developing along this International Day 9. At the same time, you can see warm water also coming out from South American coast, similar to the typical El Nino we observe during the 20th century. So this event tells us that the warm water coming out, El Nino coming out from South American coast, and El Nino showing up in the International Day 9 are 2 separate things. They are not just moving warm water from South American coast to the Day 9. They actually can happen simultaneously. That indicate that those are 2 separate phenomena. When we come to the fourth event, 2009, you can see that was one of the strongest warming in the Central Pacific during the recent few years, during the recent few decades. So now we look at the fifth event. Next one is 2015-16, which is a super El Nino event, which was on the news a lot when this event happened. But we noticed that while we see this event, if you look at the sea surface temperature evolution along the equatorial Pacific, so here's Western Pacific, Australia, here's Eastern Pacific, South American coast. So the El Nino began developing from January, February 2015 and reached the peak phase in November, December, and then die in spring of 2016. You notice that throughout the whole event, there's always a band of warm waters lingering around the international daylight 160. So when this event happened, again, we see warm water showing up outside North America, particularly near Baja California, extend all the way to equatorial at around 180. And then later in that event, the warm water come out from South American coast, join the event, and to produce this super El Nino. And when they die, they separate again because all the typical El Nino grow onset from the South American coast. As I said, when they die, they should return back to South American coast. So we see that happen, but still the warm water split into two directions. When they die, one return to South American coast, the other still stay in the Central Pacific. So the one after that strong super El Nino is 2018 and 19. Again, we see warm water coming from Baja California extended to 180 degrees at equator. So the one developing right now this year, the 2023 and 24, it looked like more like the 20th century El Nino because it has a lot of warm water coming out from South American coast. However, you notice that it also produced dual center of warming. It still maintain a separate warm water near 180 degrees. So all these 7 events we encounter it so far in the 21st century has its warm center shift to Central Pacific. So if we look at this location shift of El Nino from 20th century to 21st century can be more obviously seen if we look at the sea surface temperature anomaly evolution along the equatorial Pacific. So here I'm showing warm water sea surface temperature anomaly from Western Pacific, Australia to Eastern Pacific, South American coast from 1950s, 70s, 80s, 90s, and then the 21st century. You can see that all these El Nino event, La Nina event, blue and red, if you look at El Nino red, you can see in the 20th century, the darkest red is located inside this shading area, right next to the South American coast, all the way until we come to somewhere around middle 1990, suddenly El Nino location shift more into center at 180 degrees. You go to 21st century, beside this 1997 El Nino, you see in the 21st century, the darkest red is here in the Central Pacific. So the evidence I suggest so far indicate that our El Nino in the 20th century tend to locate in the Eastern Pacific, but for some reason, it suddenly shift to the Central Pacific during the 21st century. So in our 2007-2009 paper, we proposed one possible answer, one possible reason to explain why the El Nino suddenly shift from one location to the other location between these 2 centuries is because there are actually 2 El Nino in the tropical Pacific Ocean. So while we conduct a very extensive study on El Nino in the 20th century, because we always see El Nino coming from South American coast, so we thought that there's only one El Nino in the tropical Pacific Ocean. But actually, we suggest that there are actually 2 El Nino in the Pacific Ocean. One tend to have their warming coming out from South American coast, with most of warming concentrated in the Eastern Pacific, while the other one has most of warming concentrated near the international day-night, and with warming connect to the North American coast. So in our 2009 paper, I worked with my previous PhD student, N.G. Gao. We decide to name these 2 El Nino based on their geographic location. So the one coming from South American coast is Eastern Pacific El Nino, EP El Nino. And the one showing up in the 21st century is called Central Pacific El Nino. CP El Nino. So the other important information we suggest in our 2009 paper is that these two El Nino are different not only because their geographic location, they actually are produced by different physical mechanisms. So they're actually different climate phenomena, while they're both showing up as a warming in the tropical Pacific surface temperature that we both call them El Nino, but they actually are different climate phenomena. Therefore, the way we predict these two phenomena should be different. And that explains one thing we noticed in the ENSO research community. That is because we did a lot of research on El Nino starting from 1970. So when we come to 1990, the research community already developing very successful forecasting model to predict El Nino. However, those successful ENSO El Nino prediction model in the 20th century, when they came to the beginning of 21st century, we noticed that their prediction skill dropped. One reason is because the 21st century El Nino is a different kind of El Nino. Okay, so this is the idea we have developing a proposed in that 2009 paper. So basically, for some reason that our ENSO dynamic changed from the traditional El Nino dynamic to a new dynamic from 20th century to 21st century. That's why El Nino location changed. So we also consider that the El Nino dynamic that produced the traditional El Nino in the 20th century because it emphasized the coupling between tropical atmosphere and tropical ocean. So we decided to call this kind of dynamic tropical ENSO dynamic. While for the Central Pacific El Nino in the 21st century, its generation mechanism related to coupling process originated from North Pacific region, subtropical region. That's why we decided to call it subtropical ENSO dynamic. Okay, so our argument has been like this. So somewhere in the middle 1990s, something happened, and that will change the Pacific mean state in the Pacific Ocean, in the also atmosphere, to such an extent that ENSO dynamic shift from the tropical ENSO dynamic in the 20th century to the subtropical ENSO dynamic in the 21st century. And that explains why El Nino location shift from Eastern Pacific to Central Pacific. And so in the next two sections, I'm going to first explain what is this tropical ENSO dynamic, what is this so-called subtropical ENSO dynamic. Second, I'm going to argue that there are three possible reasons that can shift this ENSO dynamic. One is global warming here. The other is natural decadal variability related to Atlantic multi-decadal oscillation. The third factor is related to human cutting tree over the maritime continent. All these three phenomena or events can shift the ENSO dynamic from one kind to the other kind and cause El Nino to become different between 20th and 21st century. So let me first explain what is this traditional tropical ENSO dynamic. This is probably everybody well known that we also call El Nino ENSO because Jacobiacanus in his pioneer paper in 1969 realized that the ocean warming in the Pacific Ocean, which we call El Nino, is actually related to circulation change in the tropical atmosphere that we know is water circulation. And when water circulation change, it will produce pressure change across the Pacific Ocean region in atmosphere, which is known as Southern Oscillation. So he recognized that in order to explain the developing or life cycle of El Nino, we need to consider ocean in El Nino in the ocean and Southern Oscillation in the atmosphere together. That's why this concept of El Nino Southern Oscillation ENSO come up. So this terminology already automatically, implicitly thinking that El Nino is a tropical coupling phenomenon, only involve tropical ocean or atmosphere. And actually in the 21st century, outside tropical Pacific is also important. Okay, so this ENSO is the key concept for this tropical ENSO dynamic. So as I say, that because water circulation, when it got weaker or stronger, it's going to produce surface wind. For example, when water circulation is weaker than normal, then we're going to produce westerly wind across the whole equatorial Pacific. that is going to bring warm water from Western Pacific toward Eastern Pacific. Therefore, summer current in the Eastern Pacific has to be pushed down, and that will keep the cold water further away from surface in the Eastern Pacific. Therefore, it's going to warm sea surface temperature, and that's the beginning of onset of El Nino. That's why when El Nino was produced by this tropical ENSO dynamic, it will always show up first outside South American coast, and it developing throughout the life cycle. And when it dies, it will return to the South American coast. And that's our typical evolution of Eastern Pacific El Nino. So this Eastern Pacific El Nino produced by this dynamic because it relies on tropical ocean to interact with the tropical atmosphere. But now let's look at the Central Pacific El Nino in the 21st century. As I proposed, it is produced by a subtropical ENSO dynamic. The reason we argue this dynamic is because when we consider the tropical ENSO dynamic, we emphasize Walker circulation. Walker circulation has air rise over the Western Pacific maritime continent region and air descent outside South American coast. But we know that when air rise from the tropical Western Pacific, the warm pool region, it can move east to become Walker circulation, but it can also move north and south to become Hartley circulation. So that allows tropical Pacific to interact with the subtropical Pacific atmospheric ocean. So we know Hartley circulation, when the air descends to the North Pacific, is going to produce a high pressure we know as the subtropical high, Pacific high, or also known as Hawaiian high. So this high pressure typical of rotated clockwise to produce a northeast trade wind coming in the air from outside North American coast toward the equatorial Pacific. So this is the normal condition, background northeast trade wind. But if for some particular year, for some reason, outside North America, there is an anomalous southwest trade wind, which try to weaken this northeast trade wind. So the wind speed outside North America will become weaker than normal, and that will reduce surface evaporation, and that will make the ocean temperature warm up right outside South American coast. And after we have this patch warm water, this warm water is continue to excite deep convection, and then it's going to bring more air, surface air, converge into this deep convection region. So as a result, we're going to produce another new patch of this southwest wind, anomalous wind. This wind, again, is going to weaken the background trade wind here, reduce the wind speed, and again, produce a new patch of warm water. So through this wind SST with evaporation feedback process, the initial warming outside North America can continue spread southwestward toward equator and eventually produce this Central Pacific El Nino. If we look at the evolution of sea surface temperature associated particularly with this Central Pacific El Nino, we see that warm water always showing up first outside North America and then spread to international day-night and developing just locally in international day-night, become Central Pacific El Nino. And that's why this physical mechanism involve subtropical coupling. That's why I call it subtropical ENSO dynamic. So this phenomenon is produced by tropical Pacific Ocean interact with the subtropical atmosphere. So all these slides I present so far try to suggest that nature actually produce two ways to produce El Nino. So the tropical Pacific Ocean can interact with Walker circulation to produce Eastern Pacific El Nino. Tropical Pacific Ocean can also interact with the Hartley circulation to produce the Central Pacific El Nino. So those are two different phenomena, two different physical mechanisms. So during the 20th century, because our Walker circulation is particularly strong, therefore, we see a lot of Eastern Pacific El Nino. That's why we thought that there's only one El Nino. But after global warming, we weaken the Walker circulation. Therefore, this Hartley circulation mechanism become stronger, more obviously, and possible to compete with this Walker circulation ENSO dynamic. Therefore, we see more and more Central Pacific El Nino showing up. Okay, that's why I suggest that one of the reasons to cause the ENSO dynamic to change from the tropical ENSO dynamic in the 20th century to the subtropical ENSO dynamic in the 21st century, the first answer is global warming. But besides global warming, if we go back to my argument here, in order for this Central Pacific El Nino to show up more frequently in the 21st century, the other possibility is that we just ask the subtropical high, the Hawaiian high during the 21st century to become stronger than normal. So what could be the other way to make our subtropical high to become stronger? We find out that one other possible process is Atlantic multi-decadal oscillation. So we know Atlantic multi-decadal oscillation is referring to the North Atlantic sea surface temperature warmer than normal throughout the whole ocean-based region. But we know that when we notice that this Atlantic multi-decadal oscillation, if we look at the index, we know that somewhere near the early 1990s, the Atlantic multi-decadal oscillation switched from the negative phase, very cold in the North Atlantic, to become very warm in the North Atlantic. That switch happened in the early 1990s. This timing is exactly match the timing I showed you earlier, our El Nino shift from Eastern Pacific and suddenly shift to Central Pacific, also somewhere in the middle 1990s. So our argument is because Atlantic multi-decadal oscillation, when it warms up, it has a very, very strong warming center near this subtropical Pacific region of the North Atlantic. And this warm water in the North Atlantic showing up after mid-1990 is going to produce an atmospherical circulation. Warm air rise here and try to descend over the tropical Pacific region. Therefore, it's going to influence tropical Pacific ocean temperature because it suppresses the deep convection here. So here in this near the International Daylight over the Pacific, we used to have very strong deep convection. But after Atlantic Ocean warm up, this deep convection got suppressed. Therefore, it's going to produce enormous cooling. And this cooling is going to put a wave trend propagate to this North Pacific region to strengthen this subtropical high. So after subtropical high got strengthened in the Pacific, the subtropical coupling or subtropical ENSO dynamic become very strong, therefore dominate our ENSO dynamic in the 21st century. That's why our El Nino become Central Pacific El Nino, Central Pacific El Nino continuously happening in the 21st century. And the last possible mechanism can also intensify the subtropical high strength is the maritime continent deforestation. Because we're cutting tree in this maritime continent, Southeast Asia region. So after we cutting tree, we will make this land region very, very warm because we have a bare soil surface now. And if the warm soil this warm surface temperature is going to produce a local overturning circulation near Southeast Asia. It's going to produce suppressed convection right outside this Southeast Asia land area. And it's going to produce heating and cooling in this dark shading region. And this dark shading region, again, is going to send a wave trend propagate. That wave trend is going to come to subtropical high region to strengthen subtropical high again. And that's why so we did in this study, because cutting tree is only happened in the recent 20, 30 years. So we don't have enough data to prove our argument. So we use the NCAR couple model, climate model to do an experiment. In one experiment, we didn't cut a tree. In the other experiment, we completely remove all the tree over the maritime continent region. And we compared the El Nino between these two model simulation. You can see that the simulation with the tree cutting is going to intensify all sea surface temperature variation outside North America and all the way to this international daylight. That means that Central Pacific El Nino increased after we cutting the tree. So that's all the argument I want to convince you that really either due to global warming or due to nature or a human activity over the tree, over the maritime continent, or due to the nature decadal variability, AMO, our ENSO dynamics suddenly shift from Eastern Pacific to Central Pacific somewhere in the mid-1990s. So if that's the case, after we change the ENSO dynamic, all the ENSO property besides ENSO location should also be affected. The other important property of ENSO that got affected by this different ENSO dynamic is the duration. Because if we again look at this sea surface temperature anomaly along equator throughout the 20th century and 21st century, we notice that in the first two columns, the 20th century, if you look at the red and blue, red is El Nino, blue is La Nina. You tend to, in the 20th century, we tend to see blue followed by red, red followed by blue. So more often, that means that after we have La Nina, we have El Nino. After El Nino, we have La Nina. It becomes periodic or cyclic. I mean, this is very easy to predict El Nino, La Nina, because if this year is La Nina, then it's very likely next year will be El Nino. If this year is El Nino, next year will very likely become La Nina. However, if we look at the third column in this red and blue, you notice that we got a lot of blue after blue after blue, red after red after red, blue after blue. So we no longer have blue follow red, red follow blue. In the 21st century, after we changed the ENSO dynamic, our El Nino become multi-years. And that's why our El Nino prediction model failed, because they used to predict La Nina follow El Nino follow La Nina. However, in the new ENSO dynamic, it prefers to produce El Nino followed by El Nino, La Nina followed by La Nina. So let me explain why that's the case based on this dynamic. So let me go back to this traditional ENSO dynamic, that what we call a charge-discharge oscillation. So these arguments still are related to Walker circulation, but focus on the explanation more on the thermocline. So on this traditional tropical ENSO dynamic, when we have El Nino happening, we're going to produce westerly wind to the west of this warm water. And the westerly wind anomaly is going to be strongest at the equator. And that wind is going to decrease to the north and to the south of the equator. Therefore, you produce wind stress curve. That wind stress curve is going to produce ocean drop transport, try to suck all this upper ocean warm water away from the equator and bring this thermocline to more close to surface, allow cold water to close to surface to shut down this warm El Nino to become La Nina. When La Nina happens, it's going to produce enormous easterly wind. Again, the strongest enormous easterly wind is strongest along equator and weaker to the north and to the south. And that's going to produce wind stress curve and the Sibachua transport to return all the warm water from off equatorial region into equator. And after we receive a lot of warm water at the equatorial region, we're going to push thermocline deeper. Therefore, this cooling got shut down and return to warming. So by this charge recharge tropical ENSO dynamic, this dynamic prefer El Nino to be followed by La Nina followed by El Nino. So each phase can only last for 1 year. However, in my new ENSO dynamic, the subtropical ENSO dynamic, as I explained, all these subtropical ENSO dynamic, the story begins with a wind, a normal southwest wind. If you have this abnormal wind showing up outside North America to counteract with this background northeast trade wind, then the whole warm water begin to showing up and then move into equatorial Pacific to produce Central Pacific El Nino. Now, so we already have El Nino in the first year. So we already established warm water in the equatorial Pacific region. Then this warm water here is going to excite deep convection to further excite atmosphere by something we call geotide response. Then you're going to produce a pair of waves in the atmosphere right outside this warm water near the international daylight. And we notice that this atmospheric wave excited by this El Nino in the Central Pacific is going to produce, is a low pressure. It's going to produce counterclockwise wind. Again, it's going to go against this trade wind. So after we have a first year El Nino in the Central Pacific, that El Nino is going to trigger this anomalous black wind again, southwesterly wind. And it's going to trigger this coupling process coming back again. So we'll produce a second El Nino. So if you have this mechanism coming down first year, produce El Nino, this El Nino is going to further trigger the process to reactivate this ENSO dynamic again to produce a second El Nino, and this process can going on and on. So allow El Nino to become 2-year El Nino, 3-year El Nino, or La Nina become 2-year La Nina or 3-year La Nina. So my new subtropical insular dynamic doesn't require El Nino to be followed by La Nina to be followed by El Nino. It actually allows El Nino to become multi-year. And that's exactly what we see in the 21st century. Remember, I mentioned in the 21st century, 2015 and 16 is a super El Nino. So over the past 100 years, we only see 3 such strong super El Nino. One is in 2015 and 16. The other 2 are in the 1997 and 82, 83. But you can see that the previous 2 super El Nino in the 20th century, their sea surface temperature reached almost exactly the same 2.5 degrees C as the 2015 and 16. However, both events in the 20th century, in their previous year is a La Nina. So it's La Nina, after La Nina, it produces a super El Nino. After La Nina, it produces a super El Nino. However, the super El Nino in the 21st century, 2015 and 16, is actually happened after a previous El Nino. So the 2015-16 is a multi-year El Nino. Okay. Now, after 2015-16, the next El Nino is 2019 and 20. Again, you can see this 2019 and 20 is actually preceded by another El Nino. So El Nino actually started in 2018. So if you look at sea surface temperature here to plot evolution, you see that somewhere in spring of 2018, El Nino warm water already show up. It continued to develop into end of 2018. It's supposed to die, but it didn't die. It continued to develop into another El Nino, again, multi-year El Nino. So after this multi-year El Nino, we see that we have finally have La Nina come. And this La Nina instead only happened in 1 year. So after 2020, at the somewhere in the 2020, we see this La Nina happen, and it tried to die in the 2021, but it didn't completely die. It tried to grow into El Nino. So we see one red color coming out. But again, it followed by another La Nina and a third La Nina. So we have this so-called triple dip La Nina. So it was on the news a lot because this is so unique, so continuous 3 La Nina year. We only see 3 times so far in our history. And this one happened in the 21st century and caused the Australia forest fire to be very, very different from the past. Okay, so all my suggestions so far just to conclude that the 21st century El Nino is different from the 21st century El Nino is different from the 20th century El Nino because they have different dynamics. The 20th century El Nino have this tropical insular dynamic. They prefer to produce El Nino in the Eastern Pacific, prefer to have El Nino followed by La Nina, La Nina followed by El Nino. But in the 21st century, our El Nino dynamic changed to the other dynamic. It prefer to produce El Nino in the Central Pacific and allow El Nino to be followed by another El Nino, La Nina to be followed by another La Nina. So I don't have much time, so I'm going to use the next about maybe 10 minutes to just explain. If you don't care about ENSO dynamic, you don't work on physical climate, should you still concerned about our El Nino property change? The answer is yes, because our El Nino property already been different between 20th century and 21st century. That property difference showing up in the geographic location of warm water between these 2 centuries and also showing up in the duration of El Nino between these 2 centuries. And because our El Nino location changed, the way they heat up our atmosphere to produce the global impact become different. And also the duration of El Nino change is going to change the impact. So let me first just try to explain why after El Nino shift from Eastern Pacific to Central Pacific, its impact on the United States will become different. So I'm going to show this example here. So the basic argument is that in this figure, because when El Nino is the Eastern Pacific, it releases a lot of heat in this Eastern Pacific region. So atmosphere feel the heating from this location. But in the 21st century, El Nino moved to international daylight. So heat atmosphere from a different location and it sent away in a different way. And those waves propagate into North America to impact our climate. So we show that based on observation and climate model experiment, when you have warm water in the Eastern Pacific region, Then atmospheric wave, this is Z200, geopotential high in the 200 millibar. You can see that wave trend propagate from equator and coming to the United States, enter the United States first in the southwestern part of the United States, California, produce cold winter in California. And that wave trend will leave the United States from the northeastern part of the United States, produce warm winter in the Great Lake region. So when you have, in the 20th century, the California winter can be very, very cold during the El Nino year. But when we come to the 21st century, after we move this warm water to the international day-night, the wave trend in the 200 millibar propagate in a different way. It now propagate first, go to Aleutian Island and come to the United States first from the Pacific Northwest, make the Washington State, Oregon region to have a warm winter, and leaving the United States from the Florida, Miami region. So in the 21st century, during the El Nino year, the California no longer experience cold winter. Instead, it is orange grower in the Florida, Miami region is going to experience colder than normal winter. And warm winter is going to move to Pacific Northwest. Okay, so that is a very dramatic impact on our local climate after our El Nino change from one location to the other location. And it also impacts the typhoon activity over the Western Pacific region, because we know that during the El Nino years, because we warm up water in this Central Eastern Pacific region, so allow typhoon to developing, to produce, to begin to show up more eastward in the Pacific region. Therefore, they can propagate for a long time before they make landfall in the East Asia. Therefore, they can continue absorb heat to energize its strength to produce super typhoon hitting East Asia region. But when we have La Nina, we know that it's going to, the typhoon typically will, its generation is going to shift more westward because it produces cold water here because of La Nina. Therefore, typhoon need warm water to form. So typhoon is going to, or it's going to form more close to East Asia. Therefore, during La Nina year, we have fewer typhoon, and also typhoon doesn't have a lot of time to grow. Therefore, typhoon cannot be very, very strong. That was already known in the 20th century. But we noticed that in the 21st century, after we have typhoon become multi-years, after we have that multi-year El Nino, then this multi-year El Nino, then this actually after multi-year La Nina, then we see that this typhoon generation region is going to move even more close to them, and we're going to see fewer and fewer and weaker typhoon. That's why we see during the 1990 that multi-year La Nina, there's almost no typhoon activity over the Western Pacific. Okay, so finally, I just want to show this dramatic impact on the Indian Ocean, because after El Nino changed from Eastern Pacific in the 20th century to Central Pacific in the 21st century, it changed the role of Indian Ocean in our climate system. Because in the past, when we have this El Nino in the 20th century, when we have El Nino showing up in the Eastern Pacific, because this region happened to be the region is the descending branch of the Walker circulation. So Walker circulation with warm air rise in the Western Pacific, descend in this Eastern Pacific. When you have El Nino here, this warm air try to come, the Walker circulation try to come down. You see there's a warm water produced by El Nino. So this warm water prevent this the air to descend. Therefore, it's going to collapse this Walker circulation. And this reverse Walker circulation is going to bring this El Nino impact all the way to the Western Pacific and into Indian Ocean. It's going to produce high pressure over the Indian Ocean and to make Indian Ocean warm. Therefore, in the 20th century, when we have this El Nino in the Eastern Pacific, the Indian Ocean sea surface temperature variation is controlled by Pacific Ocean. It's when El Nino warm in the Pacific, Indian Ocean warm. When La Nina showing up in the Pacific Ocean, then Indian Ocean cold. Therefore, Indian Ocean doesn't have its independent active role in changing our climate. However, after we come to the 21st century, El Nino shift location to the Central Pacific. This warming is no longer in this sinking branch of Walker circulation. Instead, it moved the warm water to the middle central region of this Walker circulation. So it's no longer that capable to collapse this water situation. So in the 21st century, after our El Nino become Central Pacific, El Nino no longer can impact this control Indian Ocean temperature. So even when we have El Nino warm water in the Pacific, Indian Ocean can be cold. So in the 20th century, when El Nino Pacific warm due to El Nino, Indian Ocean has to warm. But so that allow Indian Ocean to become independent and play a more active role to changing our global climate. And so Indian Ocean has become more independent, more active from the Pacific in the 21st century. So the importance of Indian Ocean in shaping up our climate and climate variability become more more stronger and more important in the 21st century compared to the 20th century. Yeah. So there's many other different impact can be produced by after our El Nino change from Eastern Pacific to Central Pacific, after it changed from single year to multi-year, including even outside this Antarctic region. Outside Antarctic region, this sea ice formation outside Antarctic region is going to be affected also by after El Nino change to multi-year. So I'm not going through this detailed explanation. So all the results I'm showing here in this talk is wish to convey this following few key information. The first information is that the 21st century El Nino is different from the El Nino we study, we learn, or we experience in the 20th century. And this difference showing up in their property, in their generation, underlying dynamic, and in their global climate impact. Okay. And as a result of this change, the 21st century El Nino actually is more complex because it's no longer El Nino followed by La Nina, La Nina followed by El Nino. It's no longer periodic. So it's more complex and it's also more difficult to predict than the El Nino in the 20th century. And the contemporary climate model have been developed or trained to improve their simulation based on the traditional El Nino we learned from the 20th century. Therefore, all those models, they still need to catch up to revise their numerical measure, revise their physical parameterization in order to capture this new dynamic that produce this 21st century El Nino ENSO. So new effort need to make for this model also to capable simulate the 21st century new ENSO dynamic, new ENSO property, and new ENSO impact. So finally, the changing ENSO offer a great opportunity for the research community to better understand how our climate system operate. Because in the 20th century, we only thought about tropical ocean is going to influence tropical atmosphere in this climate system. But actually, the nature allow tropical ocean to interact not only tropical atmosphere, but also want the tropical ocean to interact with extratropical atmosphere in order to better allow this climate system to be able to counteract or reduce any extreme climate condition to occur. And those are the key information I wish to convey through my talk. I'll stop here. Thank you very much.
Thank you, Jin-Yi.
Thank you. So we're gonna try to accommodate question in the Zoom room, and Mary is gonna try to monitor if there are questions in Endeavor 120. And Shan, if you wanna monitor the questions on Zoom, you're welcome to. And I already see that Shep has his hand up, so we can kind of already have him ask the first question.
Great honor indeed. Jin-Yi, that was really interesting. Thanks for a great talk. I'm an atmospheric chemist, but I can still learn new things. So to ask my question, I want to ask if you can go back to the time series of ENSO events in your slides. Yeah, just
yes.
It'll take a while to get there. Yeah, up there on the upper left-hand corner. Right?
Yes. Let me bring up the screen. This one, right?
Okay, so looking at the first couple of decades, it looks to me like there's some sort of warming event. You can tell me if you want to call it El Nino in 1969 and also one in 1958. So go up to 1969 right there. No, I'm a CP ENSO event or Central
Yes.
Pacific right there.
Yes.
And there's also one, it looks like, in 1958.
Yes.
And so that's before much deforestation, before climate change revealed itself. At least for 1969, it wasn't a positive phase of the AMO. So I'm wondering if you can comment on this. Is this an expression of the natural variability, maybe in connecting with the Hadley circulation? And I also note that there's a multi-year La Nina,
Yes.
74 to 76. So is that first couple of decades expressing natural variability in the system? And that connects to, I'm sorry, a second question. Is it clear that there is a statistically significant shift? I mean, you presented it as there is a clear shift to different dynamics in the 21st century.
So the first question, yes. So even in the 20th century, we still can see this Central Pacific El Nino or multi-year to show up, because as long as we have these two type of ENSO dynamic, in some particular year when this subtropical ENSO dynamic, this what I call a Hadley circulation dynamic, suddenly become, for some reason, to become stronger than this tropical ENSO dynamic. So if we still can see this Central Pacific El Nino showing up, or La Nina showing up, even in the 20th century. So because the dynamic is still there. But overall, throughout the 20th century, the subtropical ENSO dynamic, the Central Pacific is weaker, less frequent than the tropical ENSO dynamic or the Eastern Pacific ENSO type. Yeah, but the mechanism is there, so allow this Central Pacific to show up as those two events you point out. They can still happen in the Central Pacific. So now, so that could be part of the internal variability, rather than any human activity can cause this shift of this ENSO dynamic. So I forgot, what is your second question? Could you remind me
Well,
again?
given that natural variability signal that you can see pretty clearly in the first 2 decades, is it clear that there is a statistically significant, as you put it, shift to a different, mode of variability
Right.
dynamics in the Central Pacific?
Right. Yes. So yeah, that is a good question. Yeah. So the significance examination with observational data is not there, because our observational data is relatively short. Therefore, we have been relying more on this long-term 1,000 years of couple model simulation to prove our argument. So the straight answer to your first question, there's no statistically significant evidence in observation to really prove that the dynamic completely changed from tropical ENSO dynamic Eastern Pacific to the subtropical ENSO dynamic or the Central Pacific El Nino. However, the indication, the tendency does show up in the observational data. And we also try to use the long-term simulation or model experiment to prove that, to demonstrate this possibility. Did I answer your question?
Yes, thank you.
Okay,
Appreciate
thank you very
it.
much.
Yeah, Colloqium, go ahead, and after that, Christopher, please.
Thank you. Thank you very much, Jin-Yi. I enjoyed the talk. Can you hear me?
Yes, I can hear you.
Yeah, so I want to go back to what you described about the role of the Indian Ocean.
Yes.
And my understanding, and it's not that much of my field, but there's this Indian Ocean dipole,
Yes.
which has been shown in the past to be independent of El Nino. Sometimes they coincide and sometimes not.
Mm-hmm.
But from your description, it seems to be implied that the Indian Ocean has always been locked in step with the Pacific. And I wonder how you reconcile those two schools of thought.
Okay.
Go ahead.
Thank you for that question. So yes, the Indian Ocean dipole is recognized can be a forced response to El Nino, or also can be produced as an internal mode of Indian Ocean, even without forcing from El Nino, it still can show up as an Indian Ocean dipole. But in the 20th century, the larger percentage of Indian Ocean dipole event is coincide with El Nino La Nina activity. So there's a larger fraction of Indian Ocean dipole event that is ENSO force, at least in the 20th century. But there is also, of course, some smaller percentage, but still significant fraction of this Indian Ocean dipole is independent from ENSO or El Nino. And so explain your question is that in the 20th century, a larger percentage of Indian Ocean dipole is indeed accompanied or forced by El Nino La Nina, because typically we can see after when El Nino developed during that September, October, the fall season, during the developing year of El Nino, we will see warm positive phase of Indian Ocean dipole, warm here, cold here. When we have La Nina here, more often we will see cold here, warm here. But we did observe that there are events that is independent from this El Nino. But what I suggest here, after 21st century, this Indian Ocean dipole can be even more independent from El Nino. So in the 21st century, when you have El Nino in the Central Pacific, we don't necessarily have to see positive phase of Indian Ocean dipole. When we have La Nina here, we don't necessarily have to see negative phase of Indian Ocean dipole. That was the message I tried to convey in this slide.
Okay, thank you.
Thank you.
My turn. Well, thank you. Very interesting talk. Traditional models of the Eastern Pacific El Niños emphasize the importance of ocean dynamics. So it's a coupled ocean atmosphere mode, and you actually need the dynamics of the ocean to make the thing work. In your explanation of how the Central Pacific version works, it seemed like the ocean dynamics played a less important role as more of a thermodynamic response, and that you could probably get away with, say, a slab ocean model rather than a dynamic ocean model. Is that a reasonable interpretation of your explanation?
Yes, actually, that's actually exactly accurate description of the idea related to these two types of the El Nino. So as you mentioned that the traditional Eastern Pacific El Nino produced by this discharge mechanism, it relies on sub-ocean information, thermocline variation. But in this 21st century El Nino, it only cares about mixed layer ocean. It doesn't require thermocline variation. Therefore, in this 21st century El Nino, yeah, it can get away with doing the mixed layer ocean model to produce this phenomena. But of course, in our ENSO prediction, we require both dynamics to showing up in our prediction system. Therefore, we can separately predict accurately this Eastern Pacific El Nino that rely on thermocline dynamic, and this Central Pacific El Nino that depends on mixed layer ocean dynamic. But in terms of complexity of ocean dynamic, the Central Pacific El Nino actually doesn't require very complicated ocean structure to predict. But at the same time, thermocline variation is more predictable, and mixed layer ocean dynamic is less predictable. That's why actually predicting Central Pacific El Nino, the predictability is actually smaller or shorter than this thermocline or the predictability of Eastern Pacific El Nino. Because thermocline can reflect wind or atmosphere forcing that happened, for example, 9 months or 12 months ago. Therefore, if you know summer climate variation, you can actually predict the Eastern Pacific El Nino to be show up 9 months or 12 months later. However, mixed layer ocean dynamic doesn't give you that long predictability. Therefore, Central Pacific El Nino, even though it doesn't involve this complex ocean summer climate dynamic, but its memory, its predictability actually is shorter. That's why all those prediction model, El Nino prediction model, successful in the 20th century, when they come to 21st century, their prediction skill drop because this El Nino actually is less predictable than this summer climate control Eastern Pacific El Nino.
Okay, yeah, that makes sense. Thank you.
Thank you.
Hello, it's a great talk, very interesting. So my question is actually, you answered part of my question when you answered Christopher's question. So I was asking, my first question was, you mentioned that it's the models were not as successful, but then you also mentioned that you also rely on the coupled model to sort of to verify some of your ideas. So that would suggest that the coupled model do actually simulate the two types of El Nino. So my original question was the reduced prediction skill due mostly to sort of less predictable ENSO, or is that also related to potential climate model biases? So there's a climate model bias of sort of sea surface temperature or ENSO or El Nino type SST. So would that be one also contribute to potential prediction skill degradation?
Yeah, so here come to a prediction issue rather than the underlying dynamic. So the underlying dynamic that for the Central Pacific El Nino is relatively simple because it just involves atmosphere interact with the mixed layer of the ocean. Because all my argument about how this warm water coming down from Baja California to Central Equatorial Pacific, all this process only involve mixed layer of ocean interact with the surface part of the atmosphere. So dynamically wise, it's not complicated. But for the Eastern Pacific El Nino, the traditional El Nino, it involves wind forcing and at the surface, and also not only mixed layer, but also some summer kind of the ocean. Therefore, dynamic seems to be complicated. However, because our climate model has been trained or developed based on this traditional Eastern Pacific El Nino idea, so we make a lot of effort try to make our couple model, our prediction model capable of feeling the wind forcing through the thermal climate variation. We focus a lot of this LC or atmospheric ocean interaction only inside Equatorial Pacific. Therefore, our contemporary climate model or prediction model are doing a very good job in capture those processes. Also, those processes, because ocean always lag the atmosphere, so it produce a periodic, as El Nino, always followed by La Nina followed by El Nino. So based on these two reasons, our contemporary climate model or prediction, ENSO prediction model tend to be very successful or skillful in predicting this traditional Eastern Pacific El Nino because our thermal climate representation, our ocean response to equatorial trade wind in the model has been improved a lot. However, if we when we come to this Central Pacific El Nino, dynamic-wise, it is less complicated because it only involves mixed layer ocean. You don't even need to consider thermal climate variation. However, those processes require this initial forcing coming from subtropical part of coupling system. Those signal, the initial warming outside Baja California in the model has to be able to carry through from one region gradually extending into equatorial Pacific to form Central Pacific El Nino. So this influence or this process from subtropical Pacific into equatorial Pacific actually is very difficult for climate model to capture, because this process usually this begin in March, April, May of the season, springtime, and you're developing through the summertime and eventually reach in the late summer reach to equatorial. So when we use our climate model to do the prediction, so from the prediction point of view, this actually is very difficult to capture, because you have to ensure that your prediction model is able to maintain this air-sea coupling that initially happened outside subtropical region. You need to be able to maintain this coupling, continue from springtime to the summertime, eventually 3 to 6 months. You need to make sure this warm water can really penetrate into the equatorial Pacific. So we examine a lot of these CMIT 4, CMIT 5 model. Actually, not all the contemporary couple model is able to maintain this warm water from Baja California all the way into equatorial Pacific. That's why when we use those models to do the prediction, even though the dynamic for Central Pacific El Nino is less complicated than the Eastern Pacific El Nino, but for the couple model, the forecasting model to capture this spreading from subtropical to tropical actually is very difficult. Therefore, this Central Pacific El Nino forecasting is still yet to be, it still require further improvement. So Adam, sorry, I forgot. Is that all your question, or you also ask other issue in your question?
No, I'll be discussing with you anyway. So I think in view of time, if there are other questions, I think I would let other people ask the question.
Yeah, I think we're kind of running out of time a little bit, also because there's actually a class now in Endeavor 120. So I think we're going to end the official part of the seminar. I want to thank the speaker again for a really, really interesting talk. I think there's many questions people still have. So yeah, thank you so much. And
Yep,
thank you everybody for coming. We also had 20 people actually in the room. So this was actually a pretty large audience coming that were interested in this topic. And yeah, thank you everybody.
Thank you. It's great to meeting all of you. Thank you very much.